Hybrid numbers. What are they? So in this video, I will be explaining what hybrid numbers are. And yeah, pretty much that's it. I don't have time to do anything else. So let's get started. Hybrid numbers. You might already know about the complex numbers. So numbers of the form a plus bi, where I is square root of -1. And you may also be familiar with even number systems beyond that, like dual numbers. Dual numbers are numbers of the form a plus b times epsilon, where epsilon is the square root of 0, but epsilon doesn't necessarily equal 0. So it's almost like I in that it's not a real number. Also, you may be familiar with the hyperbolic numbers, also called, I prefer to call them the split complex numbers, but in hybrid numbers they're called hyperbolic numbers. Split complex numbers, there are many other terms, there are many other terms for these numbers, for this number system. So hyperbolic numbers, like numbers of the form a plus b, generally j, or a plus b h, is what is used in hybrid numbers, but a plus bj is generally what is used, where j or h equals the square root of 1, but of course j or h is not equal to plus or minus 1, so it's almost like I the square root of -1. Now we have one for square root of 1, square root of 0, and square root of -1, but none of these, where none of the values are actually real numbers. So, also one last thing, you may be familiar with quaternions. These are also very similar. There are many types of quaternions, like split quaternions. Here I'll just write split biquaternions. What else? Dual quaternions, split quaternions, biquaternions, dual quaternions. What else? Okay, of course, quaternions are just numbers of form a plus bi plus c, a plus bi plus cj plus dk. I, j, and k are the essentially like imaginary numbers, and a, b, c, and d are real numbers. And I, j, k are just used as variables for because quaternions are useful like in jobs. Like sometimes people use them in like optics and making video games. They're just useful for visualizing things. So anyway, split quaternions, biquaternions. Split biquaternions. And of course there are other numbers like generalizations of quaternions, so like octonions, like even beyond. So there are like 8 different terms, and sedenions are like 16, and quaternions, quad 4, octonions like octo 8. So now we can get into, now that we've discussed complex numbers, hyperbolic numbers, dual numbers, and given a little bit of like a extra on quaternions and generalizations of quaternions, we can define the hybrid numbers. So hybrid numbers is C, complex numbers, union P, union D. So C, complex numbers, of course, equals set of Z. Oh, don't forget, Z equals A plus BI, where A and B are real, and I, hold on. Okay, and I squared equals -1. And then we have P equals set of OZ, or Z equals X plus, or actually, I'll use A and B. A plus B times, A plus B times generally J, or H. I'll say J, where, where H squared equals, or J squared equals 1, and of course A and B are part of the real numbers. And also we have D, dual numbers, equals this set of all Z, where Z equals A plus B, is epsilon from the Greek alphabet, where epsilon squared equals 0, and A and B are real numbers. So this is just sort of combination of all three of these, as you can see. So if you wanna describe, if you wanna reference the system of all, or the set of all hybrid numbers, use K equals number. Here, I'll just use set builder notation. A plus BI plus C epsilon plus DH is generally used, where okay, actually here, I'll do this. Here, I'll do this. So say Z equals, and K is the set. K equals set of all hybrid numbers. Oh, and by the way, hybrid numbers are actually quite new. They were developed, pretty sure, within the last 10 years. So they're relatively new. They're still being used, and they were developed by, I don't know his first name, but M. Ozdemir. I think a European mathematician. Here, I'll search it up on my computer. Oh, Mustafa Ozdemir. Maybe. Let's see. Mathematician. Might not be that. Hybrid numbers. Yeah, there are many websites. Investigation of Generalized Hybrid Fibonacci Numbers. It's pretty nice. Pretty new also. June 3rd, 2018. What else? This is something. Most of these have nothing to do with hybrid numbers. Hybrid numbers aren't very well known, but yeah, M. Ozdemir is the person who started it, and even on Wikipedia, it cites. Let's see. It cites Ozdemir M. He has a good site. He has a good website. Introduction to Hybrid Numbers, Applied Clifford Algebras, and there are some other people who already. Katoni F. Yeah. Whoever that is. But I usually see M. Özdemir. I'm talking about hybrid numbers. So, one more thing. So that was a little bit on the history of hybrid numbers. So here's another identity. So IH, let me see if this works. IH equals negative HI, which equals I plus E. Also, there's hybrid multiplication right here. It's a Cayley table. That's what it's called. These tables for for particular elements in algebraic structures. Like this is for the hybrid numbers. So I'm going to write over here so you can see. So we have 1 times 1, of course, is 1. Nothing new. Let's see. 3, 4. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Okay. We have I, square root of negative 1. We have epsilon, square root of 0, non-real. And we have h, which is square root of 1, but it's non-real. E plus I, 1 minus h, negative 1, of course. I times I is negative 1. And then we have, let's see, h, hold on. This is I meant to do I, and this is negative 1. And then we have 1 minus h, and then we have the negative epsilon, and then we have, hold on. We have h, and then we have epsilon over there, and we have I. Yeah, there we go. Now we have plus this plus I, and this, and then we have 1. H times h is 1. We have this, and then we have epsilon times epsilon is 0. And we have 1 plus h. So we got some pretty cool multiplication facts. It's I from this. And another cool thing I just saw, because these numbers are a composition of dual, complex, and hyperbolic numbers, Özdemir calls them hybrid numbers. A non-commutative two-dimensional unital algebra generated by a 2x2 matrix is isomorphic to the complex dual or hyperbolic numbers. So what is it? Commutative. Let's see. Hybrid numbers form a non-commutative rings. Non-commutative ring. And also, okay. Also, so this is it for this. I'm gonna erase this so we can get more in depth with hybrid numbers. So this is set builder notation for the hybrid numbers. So we have boldface K equals the set of A plus BI plus C epsilon plus DH, where A, B, C, D part of the real numbers. I squared equals negative 1. Epsilon squared equals 0. And H squared equals 1. Just so you can see. What else? Okay. Now it's going to get more interesting. Associative and not commutative. Okay. So now we're going to get into classifications of hybrid numbers. So let's see. character and type of a hybrid number. Okay, so we have z, let z equals a plus bi plus c epsilon plus dh. So the character is nice. There's a nice formula for a character of z equals z times its conjugate. Actually, there's a conjugate of hyperbolic numbers, which equals a squared plus b minus c squared minus d squared. And then, just getting this is pretty nice information. Z is space-like if c of z is less than 0, time-like if c of z is greater than 0, and light-like if c of z equals 0. That stuff equals 0. So yeah, these are called the characters of the hybrid numbers. And another cool thing, another way to classify them is, let's see. Oh, there's also the type number. Type number. Triangle of z, equals negative b minus c squared plus c squared plus d squared. So it's a slightly different formula. Looks quite similar though. So elliptic, I'm just gonna write elliptic triangle of z is less than 0, so the type number of z is less than 0. So hyperbolic, if it's less than 0, and parabolic if equals 0. It's type number. Another way to classify them. Also, we have the norm. So much like complex numbers, we have the norm of z, this hybrid number, equals the square root of the absolute value of the character of z, which equals square root of a squared plus, there's a formula, b minus c squared minus d squared. Absolute value of that. And then we have, that's the norm. There's also the norm of the hybrid vector of z. So we have, this is slightly different, n of z equals square root of the absolute value of the type number of z. So instead of the character, use a type number. This is different. And then, so we do the square root of the absolute value of negative b minus c squared plus c squared plus d squared Another way to classify them is the inverse. The inverse is another cool property. So z to the negative 1 equals conjugate of z over the character of z. Just going down the list. What else is cool? Let's see. Okay, so this is where pretty much the classification ends, using this Wikipedia article, because it provides the most information. This is where all the classification. This is where all the classifications of it end. So character and type. Also, we have the norms. Is another cool thing. Inverse. And then it goes to argument, polar form, de Moivre's formula, which is pretty cool. Roots, and some more stuff. Logarithm, which is what I find cool, and even Euler's formula looks pretty similar to Euler's actual formula. And so yeah, that was just a nice introduction to the hybrid numbers and what they use for. Oh, and also there's this. I find this cool. This is elliptic rotation, hyperbolic rotation, and parabolic rotation. So let's zoom in. And yeah, so that was just a nice introduction to the hybrid numbers and what they're used for, and a little bit of their history, and yeah.